Now remember, definitions are the whole of mathematics, all else is commentary, and they're so useful because every definition corresponds to a biconditional. But every equality also corresponds to a biconditional. If A equals B, then B equals A, and conversely, if B equals A, then A equals B. Does this mean every equality corresponds to a definition? It's complicated. In the game of mathematics, we agree to a set of rules, the definitions and the rules of logic, and deduce as many results as we can. If we change the rules, we change the game. We typically don't change the rules of logic, but we are allowed to use a different set of definitions. So let's play two games. In our first game, we'll use this definition of set difference. The set difference A minus B consists of the elements of A that are not in B. And let's prove the following result, that the set difference is the same as the intersection of A and the complement of B. So we have an equality, and we want to show that either set is a subset of the other. So let's suppose that X is in the set difference. By the definition we're using, this means that X is in A and not in B, but that means that X is in the complement of B. And since it's in A and the complement, it's in the intersection. And so that says that the set difference is a subset of the intersection. Now let's work the other side. Suppose that X is in the intersection. Because it's in the intersection, it has to be in both sets. And because it's in the complement of B, that means it's not in B. And so it's in A and not in B. And so by the definition we're using, it's in the set difference. And so the intersection is a subset. And now the two sets are subsets of each other. And so they are equal. Now, in our first game, a particular definition of set difference gave us a theorem. But since this theorem claims an equality, we could use it as a definition and play a game. Now, before we proceed, we note that we should be careful if we give two different definitions for the same thing. So let's discard the original definition and use only the new one. Now, we could derive some results from this new definition, but notice that if we can derive the result using the new definition, we could have derived the result using the original definition, which would have given us a new definition as a theorem, which we could then use. So this second game is included in the first game. And so we have the possibility, could the first game include more? In other words, could we derive something from the original definition that couldn't be derived from the new definition? To decide this, let's start with our new definition and see what game we can play. And in particular, we want to see if we can derive the old definition from our new definition. So using the second definition, show that the set difference consists of the elements of A that are not in B. Now note that what we're trying to prove is the set difference is the set of things where X is in A and also X is not in B. So we want to show that the set on the left is a subset of the set on the right and conversely. So suppose X is in the set difference, then by our definition, X is in the intersection of the two sets, and so that means X is in A and X is an element of B complement. But this means that X is not an element of B, so if X is in the set difference, then it's in the set defined this way, and so the set difference is a subset. Now suppose X is in the right-hand set, then by our definition of what the right-hand set is, X is in A and X is not in B, but that means that X is in B complement. Consequently, X is in the intersection of A and B complement, so by our second definition, X is in the set difference. And so our set is a subset of the set difference, and since the two sets are subsets of each other, they're equal, giving us our theorem. And this means that our second definition can derive as a theorem the result that the set difference consists of the elements of A that are not in B, but this is just our first definition of A minus B. So anything we could derive from the first definition could be derived from the second definition. Put together, using the first definition we can derive as a theorem the second definition and everything that can be deduced from it. So the first game includes the second game. Using the second definition, we can derive as a theorem the first definition and everything that can be deduced from it. So the second game includes the first game. Consequently, the two games are the same game. Now, since the two definitions give rise to the same game, they're said to be equivalent definitions. While we could keep both definitions, that's bad practice. Instead, we need to choose which is the definition and which is the biconditional theorem derived from it. Usually, but not always, there is a universally agreed upon choice of the definition and the biconditional, but remember, we can always switch them.